Hi, welcome to Math 150 Multivariable Calculus Section 2, Lecture 4. So today we're going to be talking about equations of lines and planes. And so I want to start with a problem that was requested. It is related to one that is on the homework that is due on Monday. And it'll be a good way to review some of the geometry and algebra that we've hopefully done before and lead into our discussion on lines. Later in the class, we will also review some of the trigonometry you've hopefully done before, and this is going to be a theme for how these classes are going. There's a lot of material that has been covered over the past 10 years of your mathematical careers. My exams are cumulative going back to preschool, so anything you've done is fair game. Obviously, there's going to be a preference to later material, but rather than just reviewing, you should know your rules for differentiation. You should know your derivatives. I'll try to work this stuff into the way. So you have a 4, 5, 6 triangle. And when I was young, there was a special on TV about teachers in Massachusetts who make a difference. And on the blackboard, I saw the following. And if you are a geek, if you watch a show like Big Bang or Third Watch from the Sun, you always love it when they have math in the background, numbers. Anything surprising you a little bit about this triangle? It doesn't exist. So if you take a segment of length 10, and I want one of the sides to be of length 4, I go over 4 units, and I draw a circle of radius 4. If I want another side to be of length 6, I set over here, and I draw something. So the only way that it could exist is if it's a flat line. I hope this was on the board as an example to the class of what you cannot do in geometry. I don't know because I didn't provide that much detail. But we have a beautiful relationship on a triangle. The sum of any two sides is greater than the third. If I give you a 4, 5, 6 triangle, it is a necessary condition that any two sides sum to more than the third. So this at least has a chance of existing. And then the question is that sufficient? Well, let's think about what's going on. Without also generally, I might as well assume my side 6 is at the bottom, if you're oriented that way. And then one vertex, 4 is going to come out of that, and then the other one, 5 is going to come out of that. And if you don't like the way I've done things, we'll just rotate you 180 degrees and flip. And then it will match the way you have it. So I might as well assume 4 is coming from this one. And so I draw a circle of radius 4. For the other one, coming from here, I draw a circle of radius 5. And so if I do this, I will now have my triangle, and I have found a way to construct it. How would you find the angles? If I wanted to figure out the angles, how could I figure them out? What could I use? Law of cosine. So angles from law of cosine. Okay. If we think about triangles, one thing we often look at is, well, if I have two similar triangles, maybe you saw this phrase in geometry class, CPCCC, corresponding parts of congruent triangles are congruent. And this allows me to say if these triangles have this and this in common, then they have this also in common. So does anybody remember it involves only the letters A and S, a good rule? When I can tell two triangles are similar. So A is for angle and S is for side. There are these relations. Anybody remember any of them? So SAF, side angle side. Let's think about what that is. I give you side here, then I give you an angle here, and I give you another side like that. So if I give you side angle side, is the remaining side uniquely determined? Yes. So side angle side is a valid rule. Does anybody want to say the letters of an invalid rule? ASF. All right. So let's think about what happens with ASF. I have a side here. I have an angle here. So the angle is going to give me an infinite line coming up like this. So here's the angle. Here's my side. And I have another side coming up from here. And the question is, does angle side uniquely determine a triangle? If the side is sufficiently small, is there going to be a triangle? No. So if the second side is too small, there won't be a triangle. Okay. And then as I increase the side, what eventually happens? So if the side gets, as my proposed side gets larger and larger and larger, what will eventually happen?
It will intersect.
It will intersect. How many times will it intersect?
Once.
Once. And so I will eventually come in perpendicularly, and that's the fastest way to get there. I'll hit you just once. What happens if I extend it a little bit further? I then draw a circle with that as the radius, and now I hit twice. And then we're from having no solution to 1 to actually 2.
Couldn't you have infinite though?
I'm sorry?
Oh, because I see.
Right. So for any given side length, and then the question is, well, what happens if the side keeps getting larger and larger and larger? Eventually, I'll hit the point over here, and this point's going to keep going up, and this point now will start going down there. Am I allowing that? If you allow that, you would still have 2 intersections. If not, you would only have 1 intersection up there. All right, so the old joke is you should never assume, because if you assume, that is what happens. Right, so always be careful. Angle side is not valid. Now, I like talking about this because this gives us a great way to segue into talking about the equation of a line. So here is our key point, our base point, and here is our direction. And so the question is, I want to talk about equations of lines. So you should hopefully have seen 3 different ways of writing down the equation of a line. Anybody want to give me one way to write down the equation of a line? You have to tell me what information you need to be given. Yes?
Slope intersect.
Slope intersect. So I will keep things in the same order as section 1. Slope intersect. And so the intercept is where you hit the y-axis. And how do we define the slope? Rise over run. So there's where it is change in y over change in x. And so the slope where it hits the y-axis, well, the x-coordinate would be 0 because it's hitting the y-axis. So we'll call that point 0b. And so the equation is y equals mx plus b. So that's one way. What's another way? Point slope. So for point slope, I did use some point in P naught, which is x naught, y naught. I give you a slope m, and then the equation is y minus y naught equals m x minus x. And what's the last one? One more. Point. So for point, I give you P naught is x naught, y naught, P1 is x1, y1, and I calculate, these are the givens. I like to calculate m is y1 minus y0 over x1 minus x0. And you can just use point slope. Or you could write it down the long way. Y minus y1 is equal to y1 minus y0 over x1 minus x0, x minus x0. And when you look at all of these different equations, each equation has a set of points where it's screaming at you, please look at me at this point. When you look at the slope-intercept, what would be a good choice of x to take? 0. So at x equals 0, it yields y equals b. Great. That's consistent with what we're doing. What about point slope? What would be a good point to take for x? So for point slope, what should we take for x? Is there any value of x where things might be easy to evaluate? x0. So if x equals x0, you get y minus y0 is 0, you get y equals y0. Oh, good. That's our point on the line. When we look at point, what do you think the good choices are to take for x? So for point, where should we take x? x1, and what else? I'm sorry? Nope. So x1 is one of the two values of x to try. There's one other value of x that's good to try. x0. If these are the 2 points we're given, let's make sure that they're on the line. So if x equals x0, well then this whole expression becomes 0, and we get y. Oops, there's a typo here. So if we take x, in fact, that's exactly why you want to take points to check, because you can often find out how you made a mistake. So if I take x equals x0, x0 minus x0 is 0, so this whole expression is 0. So y minus y0 is 0, so what does y have to be? Y has to be y0. Oh, that's what it is. So y equals y0. And if we take x equals x1, we get x1 minus x0 divided by x1 minus x0, that cancels. So we get y minus y0 equals y1 minus y0. Oh, okay, so y equals y1. So by checking these special cases, these show that things are reasonable. So these are the 3 standard big ways of writing down the equations of math. We want to try to find a way to write this down that will generalize. How many dimensions is a line? 1. How many dimensions is a plane? 2. How many dimensions is 3 space? 3. So when I have a line, I really have 1 to 3 parameters. The way we're viewing things in the plane is that 3 parameter is x. And once you know x, you know y. And that mostly works. So when we have an equation of a line, here is some initial point. There's a direction. When we want to calculate the slope, it's the change in y over the change in x. So this is the point x0, y0, and this is the point x1, y1. And the change in y is y1 minus y0, and the change in x is x1 minus x0. What would be a really good choice for the change in x? How much Can we always assume that the change in x is 1? We always do that for a line. Are there any lines where you can't have x changing by 1? Yeah, I was going to say, raise your hand if you think, a vertical line coming up like this. And this is why this is not the greatest way to write things down, because by specializing having x as the preferred direction, we do lose a little bit if we have that vertical line. Later in the semester, we'll do a little bit of statistics. We'll talk a little bit about regression and trying to find best fit lines and whatnot. And as long as you are not a complete moron, a certain method will work. Let's say you want to figure out how long it takes a ball to roll down an inclined plane, and you want to figure out what parameters do you think might affect how long it takes? Okay, for the inclined plane. The angle. And so you want to figure out how does the rolling time depend on the angle. And what you're going to do is you're going to lock the angle at 30 degrees and do all of your experiments at 30 degrees and deduce from that how it depends on the angle. Should you be able to say anything reasonable? No. So as long as you don't do something like that, as long as you have at least some variation in the angle, you can try to extrapolate something. How good it is, I don't know. But you can at least get something. So over here, you can associate a slope vector or direction. So sometimes instead of calling it point slope, you could call it point direction. And I'll call that vector b 1, m. And again, this is assuming the special case where we're not vertically upward. More generally, we just have some vector, and that would be the direction. Let's introduce another parameter, a time parameter. So at any moment in time, I am somewhere on the line. And so this is my line, and this is my key point, and here's the origin. I'll make the point bigger. Right. And here is my point P0. And at some later time, I'm at a new point, P. And I'll call that P of T. And here is my line direction. So the equation of the line is your location at time T is your location at time 0 plus T times that vector. We're writing it out in gory detail. X of T, Y of T is X naught, Y naught plus T times 1 plus 1 half. So I will assume we're not in the case of the vertical line. Let's see that this is actually the same as the equations of the lines that you know and love from algebra. So let's write these up. So you get x of t is x naught plus t from the first equation. If we have two vectors, the only way they can be equal is if they're equal component-wise. And then we get y of t is y naught plus nt. Well, if x of t is x naught plus t, solve for t. What is t equal? So if x of t is x naught plus t, what would t equal? X of t minus x naught. And now we can substitute that into t over here. And we'll get y of t is y naught plus m x of t minus x naught. Well, if you want to just drop the t, you just get y, bring the y naught to the other side, minus y naught is m x minus x. It's the equation of the line. So this gives us a really good way generalized what we're doing. And over here, this is just the point slope. And now we're replacing the slope with the direction. We can do this in however many dimensions we want. We have our initial point P naught, we have a direction V, and then we just flow along it for some amount of t. What might you want the length of V to be? It doesn't have to be. What might you choose for the length of V? One. Excellent choice. So then it tells you how far you want to get.
So when you draw like your little pictures with like vector V and then like point P or vector P coming up, so like where's vector V start?
So this is where things can get a little tricky. Vector V is I have moved it in space so that it's starting at the point P naught. I'm starting at the P naught, moving in the direction V. I could pick that vector up and put it down here at the origin, but it's much better for me to just locate it at the point P naught because that's where the action is happening. But the vector V is a direction vector. I'm just saying I now start at P naught and I move t units of time in the direction of V.
Thank you.
If I had a z component, all I would have to do is have x of t, y of t, z of t. It makes no difference if I have more components. And so I can do this in as many dimensions as I want. Okay. Let's make sure that this is recording. All right. So what I want to do now is, again, I want to slowly be reviewing concepts you should have been seeing in class. What's 5 times 3? That was graceful. 7 times 7. 8 times 2. 0 times infinity. Okay, did everybody say 0? Why is 0 times infinity 0?
Because anything times 0.
Because anything times 0 is 0. Anybody want to give me another answer for 0 times infinity? This is irresistible force meets immovable object. Right? What's another possibility for 0 times infinity? Infinity. And infinity beats 0. Right? Which is it? Depending on how you look at things, 0 times infinity can be anything you want. It's one of the few things that's not defined. So you should have seen limits before. We're going to be doing a bit with limits. What is the limit as x goes to 0 of x squared times 1 over x? Well, that's the same as the limit as x goes to 0 of x. What does that equal? 0. And so here, the limit of x squared is 0. The limit of 1 over x is infinity. In this case, 0 times infinity is 0. If I gave you the limit as x goes to 0 of x times 1 over x to the 4th, let's see. This is the same as the limit as x goes to 0 of 1 over x squared. What does that equal? Infinity. And now we have 0 times infinity is infinity. Somebody want to share one of their favorite numbers?
3.
3. And remember, by counting shall be 3. What movie? 4 is too many, 5 is right out. So what would be the limit as x goes to 0? 3x times 1 over x. This is just the same as the limit as x goes to 0 of what number? Of 3. So I can make 0 times infinity anything I want. It's not defined. It matters how you get there. I'm going to show you that 0 times infinity equals -1. And I will justify that to you. Anybody remember any properties of perpendicular lines from algebra? In a while.
Is the slope like a negative reciprocal?
Yes, the product of the slopes of the negative reciprocal. So if I have two lines that aren't parallel, what must be true about two lines that are not parallel? They intersect. So we're going to, Euclid's fifth, we're happy. Okay, two lines intersect. What's the location of their intersection? Where do they intersect at what point? Without loss of generality, they intersect at the... What point? Give me the coordinates.
Oh,
The origin, right? Your action is happening where they intersect. Let me choose that to be my coordinate system. So, okay, I have two lines that intersect at the origin. Again, with some imagination of some alcohol, here is a circle. There are two lines that are intersecting. And I will have intersecting at 90. I might as well choose my second point on each line to be on the unit circle. This is very similar to what we were doing in the last class. It's no longer a trick, it's a technique, it's a go-to. Put the action at the origin, look at a unit step in the direction of the action. And now by doing that, if this is an angle theta, what are the coordinates of this point over here?
Cosine theta, sine theta.
Cosine theta, sine theta. And so that's my first line, line 1. So what is the slope of line 1?
Cosine theta minus 0. Oh wait, sine theta minus 0 over cosine theta.
Sine theta minus 0 over cosine theta. So it's just sine of theta over cosine theta, which is also known as tangent. If you've ever heard of Sokotoa, that's a way to remember them. I always have to derive that because I know my trig rules, but it's sine is opposite over adjacent, cosine, no, opposite over hypotenuse. Cosine is adjacent over hypothesis, and tangent is opposite over adjacent. Sokotoa. So that's the way some people remember which formula is which. Most people earn money just showing up near poles. What is that? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. I'm old enough that we still have Pluto. So a lot of mnemonics to remember. What about the second one over here? What is the angle to get to here? So which one is 90 minus theta? Is it the angle up here, the angle here, which one? One of them is 90 minus theta. Which one? Which one? The one here,
Yeah.
yeah. The whole thing is 180. This is 90, this is theta. This has to be 90 minus theta. Easier is to use that this one is theta up here. And so if I use this one here is theta, what is the height going to be? Cosine theta. And what is the length, the vertical, I'm sorry, the horizontal displacement? No, but you're close. Very close to sine theta. Which quadrant do we live in?
Oh, negative.
Negative sine theta. So this point here is cosine of 90 plus theta, sine of 90 plus theta. This is the second line, L2. It's the same as minus sine theta cosine theta. And so we have different trig rules. So if you remember your trig, the cosine of x plus y is cosine x, cosine y, minus sine x, sine y, sine of x plus y is sine x, cosine y plus cosine x, sine y. If I put in 90 degrees, the cosine of x plus 90, well, what's the cosine of 90? 0. So one way to remember what sines and cosines are is just, draw your circle like this. And so you see if you have the cosine of 90, that's just the point 0, 1. So the cosine of 90 is this. So I want to figure out what is the cosine of 90 plus theta. I would get cosine x times 0, good, doesn't matter, minus sine x, sine of 90. What's the sine of 90? 1. And that's why the cosine of 90 plus theta, which is the whole thing we're going like this, is just minus sine theta. Okay? What's the slope of L2? So the point is negative sine theta cosine theta. So what's the slope of the second one? I'm going from here to here. What's the change in y? Cosine theta. What's the change in x? Sine theta. So it's going to be negative cosine theta over sine theta, and that's the same as negative negative cotangent theta,
Oh, yeah.
or negative 1 over tangent theta. I would prefer to write it as 1 over tangent theta rather than cotangent theta, because now it makes it very clear that the slope of L1 times the slope of L2 is negative 1. And that is a beautiful result about perpendicular lines. The product of their slopes is negative 1. We often want to find a perpendicular to a line. And so this tells me, well, if I have a point and I have a line in the perpendicular direction, its slope is just negative reciprocal of what I start with. Is this always true? Or have, yet again, you've been in a class with a professor who is glossing over some small technical cases? Is this true for every theta? Or there's some thetas we have to be careful about? Any bad thetas?
When tangent of theta equals 0.
You're right, so tangent theta is 0 because this one's going to blow up. So that's the same as sine of theta being 0. So sine theta equals 0 is bad. What else is bad? Cosine theta equals 0. So theta is 0, 90 degrees, 180 degrees, 270 degrees. Is okay. Well, what does it mean if theta is 0 degrees? They're aligned with the standard axis. So what it's saying is, as long as you're not aligned with the standard axis, the product of the slopes is negative 1. Negative 1, negative 1, negative 1, negative 1, negative 1. Don't know what it is. Negative 1, negative 1, negative 1, negative 1. So it's negative 1 everywhere except for this one spot over here. How should we define it here? Negative 1. So this is a situation where we would say that the limit would be negative 1 everywhere else. If I give you the limit as x goes to 2 of x squared minus 4 over x minus 2, this means let x get closer and closer to 2 without ever being 2. I should get closer and closer to 2 without being 2. Is there anything about this that scares you a little bit, taking this limit? Any troublesome things? So, I'm sorry?
You can cancel out.
No, we can't, but I'm saying, right now, is there anything that worries you? What you're telling me is I don't need to be worried. But what should worry me a little bit?
At first glance.
Good, at first glance, we've got a denominator of 0, and that's bad. But what's the numerator? Also 0. And so it was for Mark to subtract this. It's the limit as x goes to 2 of x minus 2, x plus 2, over x minus 2. And now it's screaming at you, just cancel the x minus 2. Because x is not 2, we can do this. So when you take the limit, it's all points that are getting closer and closer, but are never actually equal to that point. We're always moving over a small distance. Okay, now this is the limit as x goes to 2 of x plus 2. What does that equal? 4. So the limit isn't too bad to calculate in this stuff. All right, so this was a way to sneakily review some limits. And you will be doing a lot of limits when we do derivatives. We reviewed equations of lines. We reviewed this idea of move your coordinate system so that it is where the action happens. It's often a really good idea to adjust things so that you have points on a circle, because then we can write them as cosine theta, sine theta, or stuff like that. It makes it a lot easier. Yes.
When the calculation proves that you're
Well, so, right, so over here, what's the slope of the horizontal line? They get forgot to say. The horizontal line, 0. And what's the slope of the vertical line? So in that setting, if you look, so thank you, I forgot to say that. If you look at the product of the slopes, I mean, I don't understand why you guys didn't know this. I said this earlier today. A little bit over an hour in section 1. So this is one of the dangers that I sometimes forget what have I already said in this class, and I have not said that yet in this class. So thank you. I said it in section 1, but that doesn't really do much good. The product of the slopes, slope 0, slope infinity. So in this case, 0 times infinity, you can make a pitch that it should equal -1. It depends on how you do the limit. It depends how you approach. We now see why I don't want a special one direction. Because if I have a vertical line like this, I can't move x 1 unit. This is the equation x equals 5, or x equals 3. That's the equation of the line. That's vertical. So instead of talking about vectors 1m, I should really just consider a general vector. Dx, dy. And that's going to be well behaved for everything. And so what we were doing before, this special case, we can actually generalize. And so this is the equation of a line. I have a special point, I have a direction, I have a one-dimensional flow in it. Building on our wonderful, successful lines, what comes next? Plane. So now if you want to do the equation of a plane, we saw it with our coordinate system here. We have some special point P0, and maybe I have 2 directions, V and W, and that will give me a plane. And it makes sense that I should need 2 directions. A plane is a 2-dimensional object. And so one way to write down the equation of a plane is your location at time t is your initial location plus t times v plus s times w. And if you want, so this should be p of t comma s. I have 2 variables. I have a 2-dimensional object. And so what would be a good choice of s and t? What's a good choice of S and T where I should understand what's going on? 0, 0. And so if I look at what's going on at 0, 0, I get P of 0, 0 is P0. Ah, yes. That's the point where I'm defining to be the extension of the plane. That's the point where I'm defining the action to happen. So if I choose S and T to be 0, I get my plane. I get my point P naught on the plane. If I keep S 0 and I just vary T, what kind of object do I get? I get a line living in the plane going through P naught in the direction of V. Well, I could also take T to be 0, and then I'll get a line going through P naught in the direction of V. This is a plane. What comes after a plane? A hyperplane. So a hyperplane would just be a three-dimensional surface in a 4 or higher dimensional space. So instead of having TS, we would have TSU. What's the order of the alphabet?
Oh.
I mean, I would use the letter U as well. This is telling us that this is horrible notation and should be destroyed. Right? We should use T of T1, say T2, T3 would be P naught plus T1, V1 plus T2, V2 plus T3, V3. Yes.
So like, what is T?
What is T?
Yeah.
T is just your three parameters. Oh, and so here we have three parameters.
Okay, so like you have your vector V and W.
Right. So when I'm doing it like that, T would be how much I move in the V direction, and S would be how much I move in the W direction.
Oh, so it's
And
kind
so
of like,
for a line, what's the dimension of a line? 1. So once I give you one parameter T, that will tell you where you live on the line. At T equals 0, I start here. At T equals 1, I move one copy of V. At T equals 2, I move two copies of V along the line. For a plane, I have to tell you how much I'm moving in two different directions. For the plane, things get a lot more complicated. Because there's more than one choice of V and W. There's infinitely many choices. As long as V and W are not parallel, and they both live in the plane, any choice of them will work. Some choices are better than others. So again, if you think of one of the only things that I would give credit to New York City, what is a good thing that part of New York City does? The grid system. And so if you have a grid system, you'd be a fool not to measure things in north, south, east, west. But if I give you these as my two vectors, if I give you some point over here, I can flow along the line like this, and then I'll flow backwards in that line to correct it. And I can represent my point as a combination of these two directions. So as long as the two directions don't align, I can still represent everything in terms of it. Yes? I'm sorry? Yes, because they'll be intersecting at our base point P naught. We start at P naught, we have two directions coming out from it. They can't form So is it V and W don't intersect? Well, they're coming from the same point. What you really need is either they don't lie in the same direction, but they're not parallel. So as long as V and W are not parallel, as long as they're not in the same direction, they will generate a two-dimensional plane. Yes. The only trouble is if they're in the same direction. Well, if I want to get up to this point here, this vector here is the only thing that moves me up in the y direction. So I flow along it to get to the right height. But I've overshot. No problem. This vector here can fix the x direction without changing the y. So I can move backwards. And so in linear algebra, you'll do this in much greater detail. And it'll be much better. So as long as the two directions are different, we're okay.
And you don't always start in the same place.
When we're trying to use them as the directions for the plane, yes. I'm running my plane as at time Ts on my initial position plus T times V plus S times W. But there's other ways to write the equation of a plane. And this is very nice about three-dimensional space. If I give you a plane, and I give you a point on the plane, there's a unique direction perpendicular to the plane. And we call that the normal direction. So if I have a normal direction coming out, and I look at all of the things that are perpendicular to that normal direction, what kind of object is that going to span? Everything to span a plane. So another way is to give you a normal direction. So n will be the normal direction. Okay, so how am I going to do it now? I have the origin of my coordinate system. I have my point naught. Here's my plane. And here's the normal to the plane. So another way of looking at it, here's my point naught. Here's my normal. And if I take any other point in the plane, say this is the point x naught, y naught, z naught. This is the point x, y, z. I can look at the vector from P naught to my point x, y, z. And if it's in the plane, it has to form a right angle with the normal. And any point x, y, z that forms a right angle will work. So I'm getting that point by looking at x minus x naught, y minus y naught, z minus z naught. So I want x, y, z minus x naught, y naught, z naught to be perpendicular to the normal, and I like the normal as a, b, c. So this means perpendicular. If only we had a way to tell if two vectors were perpendicular. It would be wonderful if we could do that. Do we know any way to tell if two vectors are perpendicular? Dot product. So what must be true about the dot product? 0. So we want x minus x naught, y minus y naught, z minus z naught, dotted with a, b, c, and is it 0 the vector or 0 the number? 0 the number. And so if you spin it as a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. Or another way of writing it is this is ax plus by plus cz equals p naught dotted with n. Just moving the a, x naught, b, y naught, c, z naught to the other side. And if you think about it, if I tell you any two of x and y, then the third one is determined. It's a two-dimensional object. It's another way of writing this two-dimensional object. Okay. We have one last thing to cover today. We want to find normal vectors. So depending on what information you have, some quantities are easier to calculate than others. We had 3 different ways of writing down the equation of a line. And so I actually like this version, ax plus by plus cz equals something. But to do that, I need to know the normal. So imagine I give you the equation of a plane again. So let's say I give you some point P naught, and I give you two vectors v and w. And I want to find the normal. You know, any way to find the normal given v and w? Cross product. Well, at least it gives you a normal. It's v cross w. So the cross product is going to be perpendicular to the two of them. So v and w give me the plane. V cross w will give me a normal. What if I want the normal to have unit length? I don't have to, but what if I want that? What would I do? So this vector might not have unit length. What can I do? Just give up, go back to the recording? How can I fix it? And divide by what? Yeah, the magnitude, so just divide by the length of v cross w. So if you want the vector to be a unit vector, it's not a big deal. So if I give you two vectors v and w, if you want to write it in this form, that form is great if you have point normal. Well, here I have point direction. But with two directions, I can take the cross product and then I can go into this. So again, a lot of it comes down to just notation and just trying to figure out what is best. All right, so what I want to end with is just some old words and terminology just to see what you know. So what is QWERTY? That's the keyboard. Why is the keyboard set up with QWERTY1? To slow you down. In the old days with typewriters, and you had the little metal things coming down, if two ones were close to each other and went down in quick succession, they would often lock. So the typewriter was designed to slow you down by having you alternate hands with letters. Your professional typists often use the Dvorak or other keyboards. Why do we still use the QWERTY keyboard? This is the 21st century. What would we have to do if we changed the keyboard? You would have to get used to it. Do you want to get used to a new keyboard? No. And this is why you will be screwing your children someday. Just as we were screwing you, and just as our parents screwed us. Someone needs to break the cycle. It's very hard. People get used to it. It would be much better if we stopped doing the QWERTY keyboard. But some things are just so ingrained, it's hard to stop. I know everybody in this class has sent at least one email, because you all emailed me your thoughts about the graduation speech. I will assume everybody has sent an email at one point in your life where there's been more than one recipient. And oftentimes there is a privileged recipient, and where does their name go? No, that's right. That's where we're getting to, but where does the privileged person go?
About that.
In what line? In the true field. And then you can copy people with CC. What does CC stand for? Carbon copy. Why are we talking about carbon copy on an email? Anybody know what carbon copy is? Yeah. Right, so in the old days, you would have, if you want to make multiple copies of something, you would have carbon paper underneath the medium. If you go down hard enough, it would often propagate downward. And you would just pull things off, and you could give multiple copies to people. And depending on how important you are, you have a different level of readability of what you finally get. Some people have changed CC to stand for courtesy copy, excellent, because it makes no sense to talk about carbon copy in the 21st century. The last one I wanted to just briefly mention about just how hard it is to change notation and what the consequences are is on rotary telephones. When you said dial-up, this is why a lot of the area codes are what they were, is to be designed so that the people would not be confused by them, and it would be short things to dial. So if you look at how they assigned area codes to cities, it was really, in many places, inspired by having to go around a circle. So the whole point of this is oftentimes notation sticks with you for a long time, and the original reason can be long gone. All right. Have a great weekend.